3, 2, 1, and liftoff of Discovery, hoisting harmony to the heavens.
Hello everyone, today we are taking a look at the JWST's 3-month mirror alignment process. Only a few days ago Webb made history after arriving at L2. Not only this, but in the weeks prior the next generation telescope managed to complete hundreds of deployments successfully. While the JWST has already done so much in a little amount of time, its job is only just getting started. The next 3 months are very important in order for Webb to be fully operational. Starting around 4 days ago, the JWST began the final steps prior to aligning its mirror segments. This alignment process is expected to take around 3 months and allow Webb to take very clear and precise images. It will do this with multiple different actuators, wavefront sensing and control, and more. All of which helps to measure and correct any inconsistencies with the alignment of the mirrors. As many of us know, Webb is special in many aspects, including its size. While its massive size will help with gathering invaluable data, it's not helpful for the launching process. This required Webb to be folded along with each individual mirror segment positioned in a very specific way. This means as of right now the JWST's mirror is not ready to take clear and accurate images. Unfortunately for NASA, it's not as easy as just correcting the general alignment of Webb. Prior to making any adjustments, they have to measure each of the mirrors extremely precisely. In order to track any of these errors with Webb, it uses a complex system. Wavefront sensing and control is a technical term used to describe the subsystem that is required to sense and correct any errors in the telescope's optics. This is especially necessary because all 18 segments have to work together as a single giant mirror. After launch and deployment, the primary mirror segments, secondary, and science instruments will be misaligned relative to each other by up to several millimeters. An iterative process using several types of wavefront sensing and control will bring these mirrors into alignment within tens of nanometers. The large dynamic range, millimeters to nanometers, means that several distinct stages and types of sensing are necessary. This commissioning process is necessarily iterative due to finite sensing precision and also to mechanism uncertainties inherent to the core stage actuator design. As a result, optical telescope element (OT) commissioning will be iterative at both small scales. A given step may need to be performed several times to converge, and at much larger scales, mechanism uncertainties will likely require looping back to repeat entire sections of the commissioning plan. The wavefront sensing and correction process will begin once the telescope and instruments have cooled sufficiently toward their operating temperatures, expected around 40 days after launch. This process will intersperse individual wavefront sensing and control tasks, initial activation and checkouts of the science instruments, and observatory-level calibration tasks that involve many subsystems across the whole observatory, such as the guider and attitude control system. The main stages of the process are 1. Segment location and identification, 2. Segment level wavefront control, 3. Segment co-phasing, and 4. Multi-instrument sensing and control. This process, expected to take several months, comprises a large portion of the 6-month-long commissioning phase. Because NIRCam is the main wavefront sensing sensor, high-quality images will first be achieved on NIRCam, prior to any of the other instruments, about halfway through telescope commissioning. The multi-instrument sensing process then adjusts secondary mirror alignment to optimize image quality over the full instrument suite. Once the telescope is in orbit, engineers on Earth will need to make corrections to the positioning of the Webb telescope's primary mirror segments to bring them into alignment, ensuring they will produce sharp, focused images. These corrections are made through a process called wavefront sensing and control, which aligns the mirrors to within tens of nanometers. Engineers will use NIRCam to take 18 out-of-focus images of a star, one from each mirror segment. The engineers then use computer algorithms to determine the overall shape of the primary mirror from those individual images, and to determine how they must move the mirrors to align them. Engineers tested this alignment process in the cryogenic vacuum environment of Chamber A at NASA's Johnson Space Center, during about 100 days of cryogenic testing. The environment of the chamber simulates the frigid space environment where Webb will operate, and where it will collect data on never-before-observed portions of the universe. Inside the chamber, engineers fed laser light into and out of the telescope, acting as a source of artificial stars. The test verified the entire telescope, including its optics and instruments, worked correctly in this cold environment, and ensured the telescope will work correctly in space. Actuators, or tiny mechanical motors, provide the answer to achieving a single perfect focus. The primary mirror segments and secondary mirror are moved by 6 actuators that are attached to the back of each mirror piece. The primary mirror segments also have an additional actuator at its center that adjusts its curvature. The telescope's tertiary mirror remains stationary. Lee Feinberg, Webb Optical Telescope Element Manager at NASA Goddard explains, aligning the primary mirror segments as though they are a single large mirror, means each mirror is aligned to 1/10,000th, the thickness of a human hair. What's even more amazing is that the engineers and scientists working on the Webb telescope literally had to invent how to do this. These actuators are comprised of multiple different components, helping them make the necessary corrections to Webb's mirrors. I have already mentioned the general actuators, which each mirror has 7 of, 6 at the hexapod ends and 1 in the center. When the actuators at the hexapod ends pull or push on the hexapod, it pulls or pushes the mirror into the correct alignment with other mirrors. Another key component is the strut. When the center actuator moves up or down, it pulls or pushes on the 6 struts, which in turn correctly curves the mirror. Lastly, you have the electronics box. Every mirror segment has one electronics box. This box sends signals to the actuators to steer, position, and control the mirrors. These electronics boxes are positioned located within the backplane, which is the structure that holds all the mirrors. Together, each and every one of these parts work to accurately adjust 18 mirror segments to the correct nanometer. These same adjustments will be the reason the James Webb Space Telescope will produce high-quality images, rather than a blurry and distorted mess. However, this tedious process will take time to complete. Conclusion. After over a month in space, Webb is fully deployed and orbiting L2. It took multiple decades of work and billions of dollars, but the JWST is getting very close to taking its first images. One of its final steps involves finding any imperfections with each of its mirrors and correcting them. It will do this over the next 3 months using wavefront sensing and control, along with multiple actuators. Due to the accuracy of these mirror changes and the importance of correction, we will have to wait prior to seeing some of Webb's first accurate images. Until then, we can hope for the JWST's continued success, and hope to see some high-quality images in a few months. Thank you very much for watching.